going to get started now. We're working on curls and divs. I'm giving the kind of cryptic description because it's a lot easier to say and to write down, is that the curl is the cross product between the grav operator and the vector field f, and the div is the dot product of the grad operative with the vector field f. Now, a conservative field has a property that its div is equal to 0. So if you were asked, show or find out if this vector field, this 3D vector field, is a conservative field, then you just need to show that this is true. So far, so good. Right. Let me show you a little side issue. You know, you can do curls and divs for 2D. So suppose F is a vector field and it's only got 2 pieces to it, right? P and Q. But if I wanted to do the div of it, then I would do a dot product with the grad and the F. It's a dot product we'll do. The grad function is d by dx, d by dy, right? Doing a drop product of P and Q. Now you put them together, the way that works is you're not really multiplying these together, but an operator on something, so you get this guy and you get kind of that guy, right? So it is possible to do divs and grads of two-dimensional things, but we don't. Let's jump right into a couple more grads and divs, and then we'll move on to the next piece of our puzzle. I'm just scanning through here to find one. It really doesn't matter which one I find, does it? Oh, I wish I could. Does anybody know the last number I did? Do you have a copy of the number? Because these all start looking the same after a while, and I don't want to do the same one twice.
2.
Oh, say, well, that's perfect. We haven't done any worth talking about then. That's 2 just means we started it. Okay, that's fine. 3's messy, but not really hard. Do 4. So in inversion question 4, the vector field is a y cosine of xy, an x cosine of xy, and a -9 sine of z. And we're going to find the curl of f. So we set up I, j, and k. It's basically that fella, and cross product with f. So the operator delta looks like that, and essentially I'll call it P, Q, and R. P is this guy, Q is this guy, and R is that guy. So what's it going to look like? It's going to look like I, J, K, the operator again. I'm not going to do that line again, no point. And here we're going to do a y cosine of xy, and x cosine of xy, and -9 sine of z. That's not a very nice pen. Try this one. Oh, I don't need that. So many i's. Take away so many j's. Plus so many k's. I'll cover this fella up, and you get the derivative of this with respect to y, which is 0 take away the derivative of this with respect to z, which is also 0. Well, that's nice. The middle one, the derivative of this with respect to 0 is 0. Derivative of this with respect to z is 0. Take away 0 then. The derivative of this with respect to x, and then take away the derivative of this with respect to y. That's going to be a bit messier, so let's see what we get. The derivative of this with respect to x is a product rule. Okay, so if you want to differentiate that fella, it's going to be an f dash g, take away an fg dash. It's going to be a 1 cosine of xy minus an x times that, which is giving you a negative, so it's a plus xy. There you go, you get that guy. So that goes in here. And then if you take away this fella, right, going this way, you're basically going to get all the exact same thing. So it ends up being a 0. So we get 0, 0, 0. Oh, and I'm right, it is 0. Let's do change that. The curl of f that's 0. Right, let's do a div. A div of f is this guy dot that guy. So it's going to be the operator of P, Q, and R, which is going to be this guy, add this guy, add this guy. In fact, for the divergence, wouldn't that be an easier starting point, just remembering that formula? So if you differentiate y cosine of xy with respect to x, plus differentiate with respect to y, x cosine of xy, plus differentiate this guy with respect to z. Should be ready. Okay, with respect to x, that's going to get you a negative y squared, not a negative, yes, negative y squared sine xy. This one's going to get you a negative x squared sine of xy. And this guy here is going to give you negative 9 cosine of z. And so, let me reiterate my change here. The curl is a 0 vector, proves that it's a conservative field. So, by the way, isn't this guy a conservative field? Okay. Its curl is 0. Now, since it is a conservative field, let's find the potential function. And the potential function, the little guy f, has the property that the gradient of f is your vector field. Okay, so partial derivative with x, with y, and with z is going to be p, which is this guy, q, which is this guy, and z, which is this guy. So we're actually returning to something we've done in the past, which is find a potential function. Because you could use this, couldn't you, if you were going to do a line integral. We're not going to do a line integral. We're just going to find little f and call it good. So The partial derivative with respect to x matches with this guy. Partial derivative with y matches with this guy. And the partial derivative of z matches with this guy. Now, if you integrate this with respect to x, be careful here. You get y, the sine of xy, right? Y is a constant. That's like 5 cosine x's, right? So you get 5 sine x's. But that's not all you get. What else do you get because of this xy? So if you integrate a cosine of xy, you don't just get the sine of xy. What else do you get?
Another y?
Yeah, multiply or divide by it.
Would it be multiplied?
Multiply if you differentiate, divide if you integrate. So times 1 over y. Let me pause on that and show you where that's coming from. If I asked you to integrate the cosine of, let's say, 4x, because that's what we're doing, we're integrating here, you would say, oh, well, the integral of a cosine is a sine, and then when you do times a quarter, remember that? Now, if you were differentiating, it would be times 4, but when you integrate, it's times a quarter, right? They're kind of opposites of each other. So if you were going to integrate the cosine of xy with respect to x, you would also get the sine of xy, but wouldn't you also get times the derivative of 1 over that guy? Because isn't that y like the 4? Now, when you put it here then, f of x ends up being the sine of xy, because they cancel, plus an arbitrary constant that doesn't have an x in it. So some function g of y and z. Now, if you do this one, and you integrate it with respect to y, you will eventually get.
How long has your trigeminal neurons have been acting up this time?
Are we okay?
Are you in class?
Yes, I'm in class. It's been acting up for about 3 weeks now.
Right. So you've got that guy, and that ends up simplifying then down to the sine of xy again, plus some function that doesn't have a y in it. That's your arbitrary constant. And then we'll take it to the third and final one. And that's this fella here. And if you want to integrate a -9, a sine gets your negative cosine, so the two negatives cancel out, and you end up with a -9 cosine z. Essentially, I'll put it over here. So you end up with a 9 cosine of z plus an arbitrary function that doesn't have z's in it. And so we have to merge these together. So those two guys plus this guy. And there is what was called the potential function. And I'm on a roll, it's correct. Okay, so we're going to find divs and curls and potential functions. Question, Tim.
It's more of a, I don't know how to say this, a WebAssign question. Is it gonna accept the answers in IJK form, or do I need to put them in, or can I put them in the pointy bracket vector form?
Can you do it that way, or can you do that way? I'm hoping, I cannot verify this, but somebody in the class might, that it will accept both. Has anybody tried one and the other, even although it gave you the answer in IJKs, but you did it in the other way? Has anybody tried that out?
Because I really hate the pointy, or I really hate the IJK form. It's extra work to write.
Right. Well, for me, it's also a pain in the butt just to work with. Well, if you know that, if you've got this guy handy, you could type it in.
Okay.
And Do it with the brackets. I'll call these brackets. Do it with the brackets, and if it says it's good, then it's good.
I don't have
I've
web to
done
sign
it
up,
with
but
the
I'll try it.
brackets, when it's done I, J, and K.
It won't
Oh.
take the brackets, or it will.
And I haven't had a problem yet, at least.
Okay, it sounds like both are good then, which is great. Makes everyone's life easy. So next question is a version of 5, and we're given our vector function. It's y e to the negative x, e to the negative x, and then 8z. And we're being asked to find out whether it's a conservative field or not. Terence, question.
Shouldn't there be a K at the end of that last answer, that the function there?
That's here.
Yeah.
This here is an expression. So it's a scalar function. There are no I, J's, and K's in this.
I mean, like capital K, capital C, capital alpha.
Oh, like in sine x plus c, that kind of thing.
Yes.
Yeah. The way that these arbitrary constants are being taken care of, we don't need them. So we don't use them. Are they there? I think theoretically they probably are, but we just never write them. It's a bit of a bad answer, but it's the only one I can think of. So no, you don't need to put plus K or plus C. That's the answer. Okay, this guy, is he conservative or not? Well, that means essentially I have to find out. Did I go and put div when I mean curl? That guy is a zero, and if he is, it's a conservative field, and if it is, then we'll find the potential function, and if it's not, then we won't bother. So I'll set it up.
I'm just looking at it, and I'm going to make the guess that it might not be conservative, although I might just be thinking in the context of just taking you to the partial derivatives.
You are correct, it's not. That's what the answer is. I haven't found out yet why it's not, but that's what they say. They say it's not a conservative field, which means that this curl thing won't be zero. It'll be some, three-dimensional vector of some type. So many i's, taking me so many j's. Oh, here is a little trick to save you time. If the only thing the question is asking, is it a conservative field or not? If I do this guy here and the answer ends up being 5x, won't I just stop? Because wouldn't that mean it's not conservative? I don't need to go 5x, 0, 7, and then when I'm finished decide. So, okay, I'll save you 2 minutes, but it's something. All right, let's do this one. The partial derivative of this with respect to y is 0. Take away that one. Well, it's a 0, take away 0, so that one's okay. 0, take away 0, so it's not that one. So we'll have to go for this one. E to the negative x. Wait a minute, it is. Did I write the thing down?
-2e negative x.
Oh, yes. You got it. Which means it's not, which is the end of the answer. So all you would do in your homework is they ask you to find the potential function. And if it was conservative, you would actually find it. But when it's not, you write DNE. So DNE is how you get around saying it's not conservative, because there isn't a box where you click, conservative, not conservative. So you just put DNE. DNE does not exist here. But that one went okay. I'll try. Nah, it's too easy. Don't want something that's easy. This one's messy. 8. Here is our guy. We're not going to find out if it's conservative field. We're just going to find curls and divs. But I kind of like the look of this one. It's not symmetric in the sense that you can switch the X, Y's and round, but it doesn't have a cool shape. I don't want to call it symmetric because that's not really a good term for it. It doesn't have a kind of flow to it. So I have no idea what it's going to look like, but it could be interesting. I'll do the div one first. So it's differentiate with respect to X, then you differentiate with respect to Y, and then you differentiate with respect to Z. And you add them together. Right, that guy gets you e to the x. If you differentiate this with respect to y, you do not just get e to the xy. Now remember, we're differentiating here. So what else goes next to the e here? There's something missing where my finger is. The derivative of e to the xy is e to the xy times something. What goes here?
X.
Okay. So when you differentiate xy with respect to y, there's an x left. And if you do this guy, you're going to get e to the x, y, z. And then you differentiate this and you get an extra xy. So reasonably interesting looking. It's got a nice pattern to it, would you agree? Looks kind of pretty. Curl then. And operator next. And then first guy, second guy, third guy. So many I's. Take away so many J's. Plus so many K's. You differentiate this guy, you will get xz, e to the xyz. Take away nothing. You do this one, you will get yz, e to the xyz. Take away nothing. If you do the last one, you will get y, e to the xy. Take away nothing. So it's x, z, e to the xyz. Take away y, z, e to the xyz. And finish with a y, e to the xy. Let's check that out. Yep. Yep. Yep, that's right. Are finding curls and divs becoming a little bit more mechanical now, I hope. Interesting, but I'll let you do that one. Our vector field. Cosine of xz. Oh no, it's not. 0, comma. Cosine of xz, comma, negative cosine of xy. Almost missed that term, it's missing. I'll just do the curl, I won't do both this time. Zeros are good news when you do curls, because they tend to make the calculations a little bit simpler. So we get 0, we have a cosine of xz, and we have a negative cosine of xy. So many i's, take away so many j's, plus so many k's. Cover this guy up. You differentiate this with respect to y. Well, a negative cosine gives you a plus sign, and then an extra x. So that's going to be x sine of xy. Take away, well, this guy, you're going to get a negative and a sign. So that makes it a plus, and a sign with an x. So x sine xy. Excellent. Ugh, messy. Middle one. This guy is going to give you a positive sine of xy times an extra y. So y, the sine of xy. Take away nothing. And the last one's going to give you a negative z sine of xz. Take away nothing. So what have we got? We have an x sine of xy plus an x sine of xz. It's the longest one. That's a negative again, so you get a negative sine of xy. And that guy there, because I don't have room, I'll write it underneath, is negative z sine of xz. So we know that guy is...
Shouldn't that be 2x sine xy?
I'll check it.
Oh, wait.
That one.
Sorry, I missed the x.
This one. No, it's correct. I'm looking at the answer says that's the answer. So I'm good. Do you know if you find the div of that, it's 0? Can anybody remember what divs tell you? Remember that little video? What does divergence of a vector field at any given point tell you?
Was that like whether things were moving away from the point or coming towards the point?
It's the net effect of that. So it's a number, and if the number's positive, it's like a source of energy, right? Stuff is leaving it more than coming in. And it's an increase in. I don't know. If you do an analogy like it's they probably called white holes would be the name they would use in astronomy, right? At that point in space, it's a plus number, things are going out, right? Spontaneously appearing, right? Matter is negative is when it's a sink, right? Like different analogy. Can you imagine a pond where there's a fountain and a hole? Where there's a fountain, water is appearing, right? More water is appearing. And when there's a hole, isn't water disappearing? So pluses would be places where water would be gushing out, right? Like a fountain. And negative divergence would be things going in. Curls and divs, nah, done that one. Curls and divs, nah. Just plenty of practice in these ones. Curls and div, plenty of practice. Right, let's move on to 14. We have a vector field. No, I don't want to do that one. I just looked at the answer. The answer to this one is that it's not a conservative field. So I want to go to one that is. Oh, 15 is not a conservative field. Come on, give me one that is. Oh, okay. 17 is a conservative field. Let's go. So it is 5x over the square root of x squared plus y squared plus z squared. 5y over the square root of x squared plus y squared plus z squared. And 5z over the square root of x squared plus y squared plus z squared. Now, it doesn't take much imagination to know that these are really ugly things to differentiate. Agreed? So I'm going to cheat. I'm going to find the partial derivative with respect to x of that one. So I'm not doing the whole kit and caboodle because there's just too much going on here. Now, I'm going to have to fight my way through that, but I will get a partial derivative for it. But here's the trick. Once I get the answer for that, won't I be able to use symmetry to get the other two answers? So, you know, it'll take me forever and a day to do one, but at least once I've done that one, the other two are going to be free, right? So, jump into this one. Would you agree this is a quotient rule?
Yep, our good friend quotient rule. Luckily, it's not product rule. Otherwise, I'd probably forget it.
I don't know. I would probably forget it as a quotient rule. I don't see any. Well, I know it's going to come nice because I can see the answer on my screen here. I don't see how they got the answer, but at least I could. Well, I guess I could. Yeah, I could. But I just want to fight the way through this one just to show you a horrible one. But I'm only doing pieces of it. So the top guy is called F. That whole bottom thing is called G. So when I differentiate the top, I'm going to get 5, and I'm going to leave the bottom untouched. Take away, I'm going to leave that guy untouched, and now I have to differentiate that, which is a chain rule. It's 1/2 x squared plus y squared plus z squared times, well, to reduce the power by 1 to get that, times the derivative of that, which is another 2x. And the whole thing is over that guy squared. That's probably the only bit that's nice. Would you agree 1/2 power squared just gets you x squared plus y squared plus z squared, right? So if you square that, you double it. So at least that happened. Now, I'm going to leave most of this alone because the style points in this are ugly. Are you happy with the 2.5 cancelling and the x getting me x squared and the 5 getting me the 5x squared? Are we good so far? Style points, not nice. I am about to pull out 5 x squared plus y squared plus z squared to the -1/2 power as my common factor. Now we're used to pulling out common factors like x squared, right? Or 2x or 5xy. But technically a common factor only needs to be one thing. Doesn't it need to be common to both pieces? Now I've got an ugly guy to 1/2 and an ugly guy to a -1/2. And the rule for common factors still applies.
The -1/2 isn't a common factor because when you do the quotient rule, I mean, you're leaving the bottom alone, so there wouldn't be a -1/2.
But on the top, there is a -1/2 because of G dashed.
Right, but it's not a common factor between the two.
Well, I'm going to try and argue that x squared plus y squared plus z squared is a common factor of that top expression. Forget the bottom expression. Would you agree both of them contain some version of x squared plus y squared plus z squared? Right.
Yeah, but they're two different powers.
Correct, but that's okay. X cubed and x squared are common factors and they have different powers. Now, oh, you haven't seen me finish. Maybe that'll help. When I pull out the common factor from this one, you get that guy. And then you say, well, how can you pull out a -1/2 from a guy that doesn't have any -1/2 in it? Well, technically speaking, it's 1/2 subtract -1/2. So what you get is you get an x squared plus y squared plus z squared, technically to the power of 1. Now let's check that works. A negative a half times a 1, don't you get that guy back? You see how it works? If you FOIL this together, a negative a half power and a 1 power, add the powers, you get plus a half, it's this guy. So if you multiply these by that, you get this one. If you multiply these by that, you get that one. So I actually have managed to pull out a really weird common factor.
Where did the 1/2 go from the next?
It went here. It went inside the 1. So you had a half and you
No,
took
the
a negative a half
1/2
of it.
in front of the second x squared plus y squared plus z
This
squared at
one?
the top.
This one here?
Yeah, where did that one go?
Cancelled out with that too.
Oh, okay. Derp, I didn't see that.
So what I'm now going to do is leave that 5, combine these guys, and what's that? Y squared plus z squared, take away 4x squared. And that half power is going to come down here, and you're now going to get x squared plus y squared plus z squared to the 3 halves. And that, like I promised, is one ugly piece of algebra. If you bring a negative downstairs, it becomes a positive a half. 1.5 becomes 3 halves. So the partial derivative with respect to x of p, I'll just call this guy p, is going to be 5 y squared plus z squared, take away 4x squared, all over x squared plus y squared plus z squared to 3 halves. Now we're going to use symmetry to do the other combinations. Right, if the derivative with respect to x looks like this, what will the derivative with respect to y look like?
Would it be,
Well, anybody?
would it be
Go ahead,
5
Terrence.
times x squared plus z squared minus 4y squared?
And on the bottom?
That x squared plus y squared plus z squared to the 3 halves.
Correct. Is that what you were thinking, Tessa? Right. And for this one then, well, anybody want to, I'll do the bottom. I'm doing the easy bit. Okay. What will the derivative with respect to z get?
It would be 5 times the quantity x squared plus y squared minus 4z squared.
I know that was downright horrible, but at least isn't symmetry going to make the other 2 guys doable? And it's still going to be a horrendously long question. And I'm beginning to have second thoughts about actually giving it to you. It's done its job, and its job is to show you how to do with an ugly one. And since I'm in such a good mood, and there are so many of them, I'm going to kill 17. So you wouldn't need to do the rest.
Professor.
Yes.
So on the other page, the one up underneath, the one you just put under there.
Yeah.
So when you factored out the 5, what did that other portion with the x squared plus y squared? So.
Oh, yes, you're right.
So then for each one, it would just be missing the. Yeah.
Still ugly, but not as ugly. Yeah, I forgot to take out the 5 there. Welcome. So the answer just has these guys. It doesn't have the last 10 because they get killed off. Because that guy gets killed by that. Oh. I can almost see it happening. Can you imagine if you start combining these things? Won't you just get various multiples of x squared, y squared, and z squared all being, interacting in some way? So I can imagine how that would go. Little note to self, I better put that on a card. Remember to kill 17. Have you noticed that when I talk about math, it's quite violent?
Yes, it's very Scottish of you.
It is very Scottish of me. I have no idea where it started. I suspect it probably did start because, you know, like most things, isn't it the way you taught, you were being taught, stick in your head? And so I have no recollection of it, but I wouldn't be surprised if my university professors spoke about things being killed off. Well,
No,
we got,
Yankees do it too, so it must be like something in the Celtic soul.
oh, I didn't know that. Oh, you learn something new every day. Okay, we're almost finished then. So I guess I'll pick this one as our last one, which is 18. And we have x plus yz, y plus xz, and z plus xy. Would you agree that function, that vector field has a symmetry? I'm not sure if I'd use the word symmetry, but isn't it pretty? We are going to prove that this is a conservative field. Right? So, the curl of f I j k. The operator. And x plus yz, y plus xz, and z plus xy. So many i's. Take away so many j's, plus so many k's. So this should be 0, 0, 0 if things work out. Here we go. If you differentiate this with respect to x, with respect to y, you get x, and then take away an x. So you did get a 0. If you do the middle one, with respect to x, you get y. Take away with respect to z, you get y, and y take away y, it's 0. And if you go the last way, with respect to x, you get a z, and with respect to y, you get a z, and that gets you 0. Cool. So although they didn't ask this, let's find the potential function, because I think it won't take too long. So I know that this guy is going to equal f. And so I know that this guy is going to equal that one, and that one. And so the partial derivative with respect to x is x plus yz. Partial derivative with respect to y is y plus xz. And the partial derivative with respect to z is z plus xy. Now to find little f, the potential function, you integrate with respect to x. So this guy gets you 1/2 x squared. What does the term yz get you if you integrate with respect to x?
X, Y, Z.
Great, x, y, z. And the arbitrary constant is some function that doesn't have an x in it. You integrate this fella, and you get 1/2 y squared and an xyz again, plus a function that doesn't have a y in it, so I'll be xz. And then for the last one, you get 1/2 z squared plus xyz plus some function that doesn't have a z in it. And when you combine them, well, you get that guy, that guy, that guy, and one of those guys. So you get 1/2 x squared plus 1/2 y squared plus 1/2 z squared plus x, y, z. Does that look relatively pretty? Would you agree that there's a kind of symmetry in the answer? And that doesn't surprise me because there was a symmetry-like thing going on with the original. We're not doing any line integrals, but see if I wanted to do a line integral, wouldn't I just put the XYZ location at the start and the XYZ location of the end and take one away from the other, and that would be the answer to my line integral.